So good evening, everyone. Let us start today's discussion and continue from last class. So today we will be discussing basically the course content for the 11-week course, and basically this class will be dedicated for the understanding the philosophy associated with the design for torsion. So basically, we will be going through the IS code, okay, for the section containing limit state of collapse for torsion. So in this regard, we basically need in the design for torsion, we basically need two terms. One is the ME value, which is basically the equivalent bending moment, and second is the V, that is the equivalent shear force. So we shall see how we have to calculate this, and then we will uh, try to understand it better using a solve problem. So yeah, so basically for the equivalent, so basically these two are the terms which we will be dealing with for understanding the limit state of collapse for torsion. Okay. So yeah, so basically the equivalent shear force is basically calculated using this formula. Okay, so this is given in clause 41.3.1 of IS 456 in page 75. So here basically the equivalent shear force, which is V, that is equal to the sum of the shear force plus 1.6 times the torsional moment divided by the breadth of the beam. Okay, so that is V equal to Vu plus 1.6 Tu by B. So that is basically uh, how we will calculate the equivalent shear force. And similarly, we will calculate the equivalent bending moment. So that will be basically equal to the summation of bending moment at the cross section, which is the normal bending moment, and the empty value, which is the torsional bending moment. Sorry, the moment due to the torsional moment. Okay. So this empty value is equal to Tu into 1 plus d by b by 1.7, where Tu is the torsional moment. Okay. D is the overall depth of the beam, and B is the breadth of the beam. Okay. And we add it with 1 and divide by 1.7 and multiply it with torsional moment, which is the Tu value, right? So that gives us the empty value. Okay, so that is moment due to moment which has to be calculated due to the torsional moment. Okay? So adding mu and empty value, it gives the equivalent bending moment. Okay? And basically for for making the structure capable of withstanding against torsional force or moment, we basically give the transverse reinforcement. Okay, so the area like area we have to calculate for the transverse reinforcement subjected to structure subjected to torsion, so that will follow this formula. Okay, so here basically ASV is equal to Tu into SV by B1 D1 into 0.87 Fy plus VUSV by 2.5 D1 into 0.87 Fy. Okay, so this is again as per clause 41.4.3, which is in page 75 of IS 456 2000. Okay, so basically Tu is here the torsional moment, as you all have understood, and Vu is the shear force, SV is the spacing of the stirrups, and B1 is basically, if you see here, it is the center to center distance between the N rebars. Okay, so it is written center to center distance of corner bars in breadth direction. So this is the B1 distance, and D1 is similarly the center to center distance between the corner bars in the depth direction. Okay, so that is the D1. Okay, so both are required, B1 and D1, and basically either we can choose the SV value and then find ASV and bar diameter, which is normally the case, which we do. Here also in problems, we will find the reinforcement and the shear capacity using this only. And other ways we can use the we can choose the bar diameter and shear force area, shear reinforcement area, and then find the SV. So that can also be done. So normally the first way is basically suited. Okay. So yeah, so one more thing, so mu1, that is the equivalent bending moment, so that is the summation of mu and empty value. Okay, empty is Tu into 1 plus d by b by 1.7, right? So generally this empty value is generally less than mu. Okay, but if the empty value is greater than mu, then what happens, we can calculate one more term, okay, which is basically me2. Okay, So that term, that is basically equal to mt minus mu. So this the remaining part, okay, mt minus mu value, the remaining part, that gives the me2 value, okay. And that me2 value will be acting in opposite direction to the mu value, okay. So that is in opposite direction, okay. So it acts opposite to mu, okay. And that has been stated in clause 41.4.2.1 of page of IS 456 2000 in page 75, okay. So let us now understand the philosophy, design philosophy, okay, by solving a problem, okay, example problem. So let us design a simply supported beam, okay, which is having a span of 5 meter, and it is having a live load of 25 kilonewton per meter and torsional moment of 25 kilonewton meter from end to end, and the grade of concrete is M20 and grade of steel is Fe415, okay. And let us assume a clear cover of 25 and bar diameter of 25 okay. So yeah, so how we will proceed, okay. So let us say, so basically here firstly the data which is given as per the question is fck value is 20 megapascal, fy is 415 megapascal, l is 5 meter, the wll value is 25 kilonewton per meter, and torsional moment is 25 kilonewton meter, right. So that is the first the data, okay. So now let us calculate the load, okay. Now let us calculate the load that will be acting. So the live load we know, that is 25 kilonewton per meter, which has been given. Now let us first calculate the dead load, okay. So dead load will basically it will be basically due to the self weight, right. So for this, let us first assume the width of the beam, okay. So let us assume that the width of the beam is 250 millimeter, okay. So as per as per IS code, okay, in case of simply supported beam, so the span by depth ratio should always be less than equal to 20, okay. So that should be the maximum value. So using this condition, if we see, we can calculate the depth, okay. So span is 5 meter, okay. So basically depth will be equal to 5000 by 20, which is equal to 250 millimeters, right. So that is the minimum depth, okay. So that is the minimum depth which should be provided. It should not be more less than this. If we provide less than this value will be more than 20, right. So it should be the minimum depth, okay. So let us assume the overall depth is 500 millimeter. Let us take it twice, okay. So therefore if we take the depth as total depth as 500 millimeter and width of the beam is 250 millimeter, and then if we find, we will see what will be the self weight. It will be equal to 0.25 into 0.5 into 25. 25 is the unit weight of concrete, right, RCC, 25 kilonewton per meter cube. So it will be 0.25 into 0.5 into 25, which will be equal to 3.125 kilonewton per meter, okay, per meter length, okay. So per meter length it will be 3.125 kilonewton. And therefore the factored load, okay, the design load or the factored load we can calculate, okay. So we know the dead load, which is 3.125 kilonewton per meter. We know the live load, which is 25 kilonewton per meter. So therefore the design load will be 1.5 times 3.125 plus 25, okay. So that comes out to be equal to 42.1875 kilonewton per meter, right. So basically we have got the design load, okay. So using the design load, we can calculate the mu value, which, okay, which is the basic the bending moment, okay, bending moment due to the basic loads, the dead load and the live load, basically the design load, okay. So in case of simply supported beam, what is the maximum bending moment? That is nothing but WL square by 8, right. So the UDL W value is 42.1875, L value is 5 meter. So mu value will be equal to 42.1875 into 5 square divided by 8, okay, which comes out to be 131.83594 kilonewton meter, or we can write it as 131.84 kilonewton meter, right. So that is the value we have calculated, mu value we have calculated, which comes out to be 131.84 kilonewton meter, okay. Now the torsion value is given as 25 kilonewton meter, okay. So this is the torsion value, and we will try to calculate the design. This is the design torsion value, so that will be factored torsion value. So that will be equal to 1.5 times into 25, which will be equal to 37.5 kilonewton meter, right. So that is the torsional moment. So using this we can calculate the equivalent moment due to torsion, okay. So this equivalent moment torsion due to torsion formula, which is tu into 1 plus d by v by 1.7, right? So putting the values into the variables, okay, tu plus 1 tu into 1 plus d by v by 1.7. So here tu is 37.5, capital D is 500 or zero point 0.5, b is 250 or 0.25, okay, because it is it will cancel each other, so we can write either in millimeters or meters. It will remain the same, okay. So putting the values, we get 37.5 into 1 plus 500 by 250 divided by 1.7, which is equal to 37.5 into 3 by 1.7, right? So it will be equal to 37.5 into 1.7647. So it will basically come to be 66.176 or 66.18 kilonewton meter. Okay, so that will be the equivalent moment due to torsion, which is 66.18 kilonewton meter. Okay. So therefore, we know the mu value, that is the factored moment, and the factored moment, and we know the equivalent moment due to torsion. The factored moment is 131.84, okay, and equivalent moment due to torsion is 66.18 kilonewton meter, okay. So therefore, what will be the equivalent bending moment? It will be the summation of both this, that is 131.84 plus 66.18, okay. So adding both this, we get 198.02 kilonewton meter, okay. So that is basically the equivalent bending moment, okay, which is there because of the torsion acting, okay. So total equivalent bending moment. So this is 198.02. So using this, okay, using this we can calculate the required effective depth or the minimum effective depth which is required, okay. So we know that the limiting value of moment from the concrete side, it is or compression side, it is basically 0.138 FCK BD square, right? So putting the values, FCK is 20, B is 250 mm, D we have to find, and M is 198.02, right? So putting these values, we get the D value equal to 535.71 millimeter. So we are getting the minimum required effective depth as 535.71 millimeter, okay. But if you see here, we have taken the overall depth as 500 mm, okay, which is lesser than even the effective depth, okay. So it is lesser than the effective depth, okay. So therefore, it or the effective depth is not less than the actual overall depth we have taken, okay. So that means our section is not okay, it is not correct, so we have to redesign, okay. So the best way to redesign is, let us take this effective depth only as the effective depth, okay, and we have taken, assume the clear cover is 25 mm and the rebar diameter is 25 mm also. So therefore the overall depth will be how much? It will be 25 plus half of 25 plus 535.71 millimeter, which comes out to be 573.21 millimeters, right? So that is the overall depth, okay. So that is the overall depth. So instead of 573.21 millimeter, we can also take overall depth as 575 millimeter, okay. So if we take the this one, if we take the width as 250 millimeter, so we have to provide an overall depth of 575 millimeter for a proper design, okay. So that is the case. But let's say 575, okay. So it is not, although it is multiple of 5, but it is not a very unique like rounded number, okay. So it is a multiple of 5, okay. So generally we don't provide like this dimension, okay. We always provide in multiples of 10, okay. So therefore and also if we go for that, it will be increase, the depth will be increasing, okay, unnecessarily. So that also means uneconomy, okay. So keeping all these factors in mind, let us increase the width of beam into to 300 mm from 250 mm, okay. So let us assume the width of beam has been increased from 250 to 300 millimeter, okay. So in that case, what will be the case, okay. So we have taken the overall depth again as 575 mm from the last case, okay, and we have increased the width of beam to 300 mm. Now let's see what is the difference. So the ME value, that is the equivalent moment only due to only torsion, okay. So that is equal to tu into 1 plus d by v by 1.7, right? So tu value is 37.5, which we have calculated already, and into 1 plus d we have taken as 575, and b this time we have taken as 300, okay. So divided by 1.7, so this comes to be 60, comes out to be 64.33 kilonewton meter, right? And the self weight, okay, so that also we have to calculate again, because we have increased this to 0.3, right? The 300 from 250, okay. So self width will definitely increase this time. So it will be zero point 0.3 into 0.575, and also the depth also increased. So it will be zero point 0.3 into 0.575 into 25, which comes out to be 4.3125 kilonewton per meter. Okay. So therefore the design load will be the addition of this and the live load, which is 25 into 1.5, right? So it will be 1.5 into 4.3125 plus 25, which is 43.96875 kilonewton per meter. Okay. So the mu value this time, okay, so that will also it will be also changing because the w value has changed. Okay, so initially it was how much? Initially it was 42.1875, right? But now it has increased to 43.96875, basically due to the increase of the width. Okay, so it has increased the w value. So therefore we have to calculate again the mu value, which is 43.96875 into 5 square divided by 8. Okay, so that comes out to be 137.40234 kilonewton meter, or 137.40 kilonewton meter, right? So therefore this is the mu value and that is the me value. Okay, so therefore the equivalent bending moment, it will be the addition of this and this, that is 64.33 plus 137.40. Okay, so adding both we get the value of equivalent bending moment as 201.73 kilonewton meter. Okay, so taking this as the m value now and finding the effective depth. Okay, so if we find this, so it will come out to be square root of 201.73 into 10 to the power 6 divided by 0.138 into 20 into 300, right? So this comes out to be 493.59 millimeter. Okay, so it is much less. Okay, so in this case, this is the effective depth. Okay, so now if we find the overall depth, okay, total depth, it will be 493.59 plus 25, which is the clear cover we took, and plus 25 by 2, which is the half of the rebar diameter. Okay, so that will be coming out to be 531.09 millimeter. Okay, so we took the effective depth or the overall depth as 575 millimeter, and we require the minimum required of overall depth as 531.09 millimeter. So if you see here, there is a difference of around 45, right? 45, 44 millimeter. So we are giving more than required. Okay, so it's uh, uh, better to take a value which is one. Firstly, it is better to take a value which is multiple of 10, and secondly which is near to this value for economy. Okay, so instead of 575 millimeter, let us provide overall depth of 550 millimeter for an economical section. Okay, so let us provide overall depth of capital D equal to 550 millimeter. Okay, so in that case, the self weight will again change. So it will reduce basically. So instead of 575, we have taken 55, okay, or 550. So yeah, so the self weight will become zero point 0.3 into 0.55 into 25. Okay, so that will be equal to 4.125 kilonewton per meter. And because it has changed, again we have to find a dead load, a design load, which is equal to 1.5 into 4.125 plus 25, right? So that will be coming out to be 43.6875 kilonewton per meter, and therefore the mu value will be equal to again WL square by 8. So W value is 43.6875. L is 5. Okay, so it will be 43.6875 into 5 square divided by 8, which is 136.52 kilonewton meter. Okay, so that is the mu value, right? Now the equivalent bending moment due to torsion, okay, so that will be equal to 37.5 into 1 plus 550 by 300 by 1.7. Okay, so because we have changed the section, we have taken it as 550, so we have to again calculate the equivalent bending moment also for torsion. So that will be equal to 37.5 into 1 plus 550 by 300 by 1.7. So that comes out to be 62.5 kilonewton meter. Okay, so again, so if you see the equivalent bending moment, so it is 136.52 plus 62.5, which comes out to be 199.02 kilonewton meter. Okay, so now this is the this section is ideal. Okay, so this section is ideal because if you calculate here the effective depth also, the required effective depth. Okay, so it will be it will be lesser than what we have taken. Okay, so we have taken effective depth of overall depth of 100 and we have taken overall depth of 550 so effective depth will be around 515 Okay, so if we find this value also, so because In 201 only it is 493. Okay, so for 199 it will be even lesser. Okay, it will be around 492 or something, 490. So for 490 mm we have taken 515 or 520 mm effective depth, so therefore our section is okay. Okay, so that is basically the dimension, the concrete dimensions are okay. Now let us go for the design of steel. Okay, so we have got the limiting moment value as 199.02 kilonewton meter, right? And we have taken the effective width as 300 millimeter, right? The FCK value is already given as 20 megapascal. The FY value is given as 415 megapascal. Okay, and the overall depth is 550 millimeter, right? So yeah, so let us assume that instead of, like, they have assumed that should not be like, we could have gone by 25 mm only, but they have assumed it to be 20 mm. Okay, the rebar diameter in this case. So instead of taking 25, let us take it 20. Okay, so please understand the design philosophy. So that is the whole idea. Okay, for that discussion. So D value is 550 millimeter, which is the overall depth, and effective depth is 550 minus 25 minus 20 by 2. Okay, so it will be 515 millimeter. Okay, so that's what I told you. So it will be like the required value would have been around 490, 492, but we have taken 515, so therefore it is okay. Okay, so okay, so it is shown here also. So D computed value is, the required value was 490 mm. Okay, so 199.02 into 10 to the power 6 by 0.138 into 20 into 300 square root, so it comes to be 490 mm, but we have taken 515 mm, so our section is okay. Okay, so now we need to find the basically, for calculating the area of steel, we need to find the lever arm z. Okay, so z is equal to what, d into 1 minus 0.42 x by d, right? So therefore we have to calculate the x by d value. So x by d is equal to this formula, which is 1.2 minus 1.2 square minus 6.6 mu by fck bd square whole to the power half. So this formula is very important. Okay, it is already always required in the design, so please memorize this formula or write it down somewhere. Okay, so it is a very important formula, okay, for the design, mainly for the calculating area of steel. Okay, so here we have taken the FCK value as 20 megapascal, the B value is 300 millimeter, the D value is 515 millimeter, and MU value is 199.02 kilonewton meter, right? So substituting the values, we will get the x by d value equal to 1.2 minus 1.44 minus 0.8254 whole to the power half equal to 1.2 minus 0.6146 whole to the power half equal to 1.2 minus 0.7839. So it comes to be 0.4161. Okay, that is the x by d value. So therefore the lever arm z, that is equal to d into 1 minus 0.416 into x by d. Okay, so d value is 515. Okay, x by d is 0.4161, which we just calculated. So substituting the values, we get the lever arm value as 425.85 millimeter. Okay, so now the limiting moment taking from the area, from the steel side or the tension side, so it is equal to 0.87 fy ast into z. Okay, so that is the value of mu. So substituting the values of Fy, Z and Mu, we get the area of steel. Okay, so Mu is basically 192.02 into 10 to the power 6, right? Fy is 415 and Z is 425.85. Okay, so substituting the values, we get the area of steel as 1294.4 millimeter square, or simply 1294 millimeter square. Okay, so that is the area of steel required, so which is 1294 millimeter square. Okay, so we know that area of 1 mm dia 20 mm dia rebar, it is equal to 314 millimeter square. Okay, an area of 116 mm dia rebar, that is equal to 201 millimeter square. Okay, so if we take 20 mm rebars and 216 mm rebars, so that will be equal to 3 into 314 plus 2 into 201, that will be the area. Okay, so which is equal to 1344 millimeters square. So this was the area which was required as per the calculation, and we have if we take 20 mm and 216 mm dia rebars, we will get an area more than the required. Okay, so that is okay. Okay, so therefore let us provide 320 mm dia and 216 mm dia rebars. Okay, in the tension side. Okay, as shown in the sketch. Okay, and therefore the percentage of steel will be in this case equal to the AST given value, provided value, divided by B into small d. So AST provided is 1344 and B is 300, D provided is 515, right? So it will be into 100, we get the value of percentage of steel as 0.869%, which is basically the PT value. Okay, so now if we see here, the equivalent bending moment due to torsion, this value was 62.5 kilonewton meter, right? And the bending moment value, so that is mu equal to your it was 136.52 kilonewton meter. Okay, so if we see here, so basically this, yeah, so basically this value is basically for the tension side. Okay, so that is the downward side, okay, or tension side. Okay, so like the bottom side. Okay, now let us see in this case. So this for this like we have provided the area of reinforcement in the bottom side. So now also let us see what is the area of tension that is required, area of rebar that is required in the compression side, or basically the compression steel that is required. Okay, so for that, finding that, we have to only consider the torsional equivalent moment, not the mu value. Okay, because this because as we all know, the mu value will be taken by in the compression side, it will be always taken by the concrete, and in the tension side it will be taken by the steel. Okay, but in the case of torsion, okay, torsion, so because the torsion is basically what it is, a twisting moment. Okay, so therefore that moment has to be resisted by both the tension as well as compression side. Okay, and for that we definitely need rebars. Okay, so which is the extra. Okay, because we can provide it through concrete. Okay, so like the doubly reinforced bars, we have to provide it using rebars. Okay, so we have to provide compression steel. Okay, so for that we need the mu value of torsion only, like mu equivalent value of torsion, not the total m equivalent value. So therefore we have to remove the mu value of 136.52. Okay, so from 192.02, if we remove 136.52, we get this. Okay, so this is the value we require, which is basically the equivalent moment due to torsion, which is 62.5 kilonewton meter. So using this, we will calculate the x by d value for the area of steel in compression. Okay, so this is the area of steel in tension. Okay, now let us see what is the area of steel in compression. So first we'll calculate the x by d value. So that is equal to 1.2 minus square root 1.44 minus 6.6 mu by fck bd square. So this is an important formula. Please memorize and keep it, write it down separately. So mu value is 62.5 into 10 to the power 6. fck value is 20. B is 300 mm and D is 515 mm, right? So substituting the values, we get the x by d value equal to 0.1102. Okay, and putting this value here, okay, in the AST formula, okay, limiting moment formula from tension side. So that is this should be actually AC in this case. Okay? So it is 0.87415 into 1 minus 0.1102 into 0.416 into 515. Okay, so into AST equal to 62.5 into 10 to the power 6. So therefore AST or AST value comes out to be 352.55 millimeter square. So if you see, it is much lesser. Okay, so here it required was 1294. Here we only require 352.55 millimeter square area. Okay, in the compression side. Okay, so and basically the compression side is always in the top, right, in the case of beam. Okay, so yeah, so if we see here, basically if we see here, so 16 mm, if we take 2 mm dia reverse, it will be 402 mm square, so which is greater more than the required value. Okay, so we can give 216 mm. If we take 20, it will be much more. Okay, so it will be uneconomical. So let us take 402 only, that is 216 mm dia bars. So we will provide 216 mm dia bars at the top. Okay, so we will provide at the bottom 216 mm and 320 mm. Okay, and in the case of uh, yeah, so we'll provide 216 mm and 320 mm at the bottom, and in the case of this one at the top, we will provide 216 mm. Okay? And like this only, because of this only, the rebar diameter we have changed. Okay, initially we assumed it to be 25 and made calculations with that, and finally when it was seen that, you know, we don't like 225 is much more. Okay, that will result in uneconomy, so we have changed into 16 and 20. So we have changed the rebar diameter as 20. Okay, so and here like, so therefore in tension side we will be providing 216 mm plus 320 mm dia rebars, and in the compression side, which is at the top, we will be providing 216 mm dia rebars. Okay, So basically that is the design. Okay, so that is the design for torsion. Okay, so with torsion there is also shear part also acting. Okay, so let us see what how we have to deal with the shear. Okay, so that is basically the torsional that was the design basically for the torsional moment part. Now we have to see the design for the shear part. Okay, so the W value which we calculated is 43.6875 kilonewton per meter. Okay, which was the design load. So VU value will be coming out to be 43.6875 into 5 by 2. Okay, so that will be that is WL by 2. Okay, for simply supported. So it is equal to 109.218 kilonewton, and torsional moment is 37.5 kilonewton meter, right? So therefore the equivalent shear force V value, okay, so that is as per the formula which was basically V equal to VU plus 1.6 T by B, right? So VU value is 109.218, okay, 1.6 into TU value which is 37.5, and B value is 300, okay, or zero point 0.3. Now here you can take 300 because this will not like we have to cancel millimeter meter and meter, okay. So therefore it has to be zero point 0.3, okay. So yeah, so substituting the values we get the V value equal to 109.218 plus 200, which is 309.218 kilonewton. Okay, that is the equivalent shear force. Okay, now so we got the equivalent shear force. So from that we will calculate the equivalent shear stress. Okay, so which is equal to VE divided by B into D. Okay, so V is 309.218 kilo into 10 cube. Okay, that is Newton, divided by 300 into 500 millimeter square. So that comes to be 2 Newton per millimeter square, 2 megapascal. Okay, and that value is less than the maximum strength of concrete as per table 20 of IS 456 for M20, which is 28 megapascal. So because 2 is less than 2.8, so the section is okay. Okay, so now we have to find uh, the shear strength of concrete. Okay, so that for that we have to go to table 19 of IS 456, as we have already discussed this in previous classes. So for PO equal to 0.869%, okay, so we get the gamma C value equal to 0.56 plus 0.62 minus 0.56 by 0.25 into 0.869 minus 0.75, so which comes out to be 0.5885 megapascal. Okay, so that is the shear strength of concrete. Okay, so as you can see this value is less than the equivalent shear stress which is acting. Okay, so therefore we have to provide shear reinforcements, which is mandatory. Okay, must. So let us see how. So let us assume the spacing of stirrup reinforcement as v as 190 millimeter. Okay, so let us assume this value. So you can also take some different value, but then you have to find the conditions and we have to satisfy all the conditions. So we have found, like it has been found that if we take 190 mm, the conditions are satisfied. Okay? So that's why we can go with this value. So let us see. So the area of shear reinforcement which is required for the torsion case is calculated using the clause 41.4.3 of IS 456, which is present in page 75. So as per that, the area of shear reinforcement equal to TU into SV by B1 D1 into 0.87 Fy plus VU SV by 2.5 D1 into 0.87 Fy. So this we have already discussed in the initial slides in today's class. So B1 value here we can find out, that is equal to 300 minus 25 minus 20 by 2 minus 20 by 2. That is this case. Okay, so that comes out to be 230 millimeter, and D1 is basically 550 minus 25 minus 20 by 2 minus 16 by 2, because we have provided only 216 mm. Okay, so and clear cover is 25. So this D1 value is 482 millimeter. Okay, so substituting all these values in this equation is formula, so we get the ASV value equal to 225.70 millimeter square. So that is the area of shear reinforcement that is required. Okay, now the minimum ASV value, okay, the minimum shear reinforcement value, that is calculated equal as using this formula, which is equivalent shear stress minus concrete shear strain into B into SV by 0.87 Fy. Okay, so gamma E value is 2, as we all know, we have found, and gamma C value is 0.5885. Okay, B is 300, SV we have taken as 190, and Fy value is 415. Okay, so substituting these values we get the ASV minimum as 222.84 millimeter square. Okay, which is less than the ASB we have provided, okay, so which is 225.7, okay. So therefore the section is okay. So if you would have taken 200 mm, okay, so if you would have taken 200 mm, this would not be the case, okay. This would be the minimum required, would have been minimum value would have been greater than the required value, provided value, okay. So minimum required value would have been greater than the provided value, so we had to redesign, okay. So therefore we took it as 190 mm. So if you see, if we take 190 mm, the minimum required value is less than the provided value, so the design is okay, okay. So now let us give the shear reinforcements. So if you see here, if we take one 10 mm dia rebar, so its area is 78.5 mm square. If we take 12 mm dia, area is 113 millimeter square. And if we take 1 mm 116 mm dia rebar, the area is 201 mm square. So we need 225.7, okay. So this is almost twice of this, okay. So if we take 213, okay, or two-legged 113, 2 into 113 is 226, which is greater than the 225.7, okay. So therefore if we take two-legged 12 mm dia, okay, at the rate 190 mm center to center, so our shear reinforcement will be okay, okay. So good, it will be good. And if we take 201, it will be uneconomical, okay. So let us take 113, that is 12 mm dia. So therefore let's provide shear reinforcement as 12 mm dia, two-legged, at the rate 190 millimeter, okay, center to center basically. So yeah, so basically this is the summary of the design, the whole design. So basically we can provide the overall depth is 550 millimeter, okay, the width equal to 300 millimeter, the clear cover equal to 25 millimeter, the grade of concrete is M20, grade of steel is Fe415, okay. The bottom reinforcement, it can be given as 320 mm dia and 216 mm dia, and therefore the area of steel provided will be 1344 millimeter square with a PT value of 0.869%, and the top reinforcement that will be equal to 216 mm dia, okay. We will be providing at the corners, and the area of steel provided will be 402 millimeter square, and therefore the shear, and also the shear reinforcement will be equal to we will be providing 12 mm two-legged 12 mm dia rebar at the rate 190 millimeter center to center. So that will be the condition for the stirrups, okay. So we will be providing 12 mm dia two-legged at the rate 190 millimeter center to center stirrups, okay, as shear reinforcement. So that is the whole design, okay. So with this we have come to the end of the course content discussion. So now let us now let us enhance our understanding by a few solved problems, okay. So the first problem is, as per IS 456/2000, the maximum shear stress for M25 grade of concrete is A 2.5 megapascal, B 2.8 megapascal, C 3.1 megapascal, or D 3.5 megapascal. Okay. So what is the maximum shear stress for M25 grade of concrete? Okay. So that this is as per table 20. Okay. So we have to check table 20 of IS 456, and if we check there, which is in page 73, we find that the maximum shear strength of concrete for M25 grade is 3.1 megapascal. Okay, so that is the maximum shear strength of concrete. So C is the correct choice. So as you can see, C 3.1 Newton per millimeter square is the correct option. Okay. Second question: a rectangular beam cross section having width as 400 millimeter and effective depth as 450 millimeter is subjected to a design torsional moment of 120 kilonewton meter and transverse shear forces of 50 kilonewton. The equivalent shear stress for which the section is to be designed is A 3.1 megapascal, B 1.5 megapascal, C 1.75 megapascal, or D 2.94 megapascal. So if we see here, we know the formula of equivalent shear force, that is V equal to Vu plus 1.6 Tu by B. Okay, and we need to calculate the equivalent shear stress, which is tau V. Okay, so that is equal to V by Bd. So initially we will calculate V. Okay, so Vu value, the given values of Vu is how much? Yeah, so it is 50 kilonewton. Tu value will be 120 kilonewton meter, okay, and B value is 400 mm or zero point 0.4 meter, okay. So substituting the values, the V or the equivalent shear force is 530 kilonewton, okay, and B value is 0.4 or 400 because it is we have to convert in millimeter, okay. So this is 530 into 10 cube, and B is 400, and effective that is 450, okay. So it is 530 into 10 cube by 400 into 450, which comes out to be 2.94 megapascal, okay. So therefore D is the correct option. So as you can see, D 2.94 megapascal is the correct option. Okay. Third question: a rectangular beam cross section having width as 400 millimeter and overall depth as 500 millimeter is subjected to a design torsional moment of 120 kilonewton meter and bending moment of 130 kilonewton meter. The equivalent bending moment for which the section is to be designed is nearest multiple of 5. So like what will be the equivalent bending moment at a nearest multiple of 5? Okay. So will it be A 320 kilonewton meter, B 200 kilonewton meter, C 290 kilonewton meter, or D 250 kilonewton meter? Okay. So what will be the option? So if you see here, the equivalent bending moment MUC, so MUE, okay. So that is as we discussed, it is a summation of MU, okay, the factored moment plus the equivalent moment due to torsion, which is TU into 1 plus D by V by 1.7, okay. So MU value as has been given is 130 kilonewton meter, okay, and torsional moment is 120 kilonewton meter. D value is 500, capital D is 500 mm or zero point 0.5, and B is 400 mm or zero point 0.4. Okay, so we can write both because it will cancel and units will cancel, and divided by 1.7. So it is 130 plus 120 into 1 plus 500 by 400 by 1.7, which just comes out to be 288.82 kilonewton meter. Okay, so therefore if we see the nearest multiple will be 290 kilonewton meter. Okay, so therefore C is the correct option. So C 290 kilonewton meter is the correct option. Okay. Fourth question: a rectangular beam cross section having width as 400 mm and effective depth as 450 mm is subjected to a design torsional moment of 120 kN and transverse shear force of 50 kN. If the spacing of the shear reinforcement provided, grade of concrete, grade of steel, and percentage of tensile reinforcement provided are 130 mm M25 Fe415 and 0.25% respectively, what would be the minimum area of total transverse reinforcement as per IS 456 2000? A. It should not be less than 125.07 mm square. B. Should not be less than 371.58 mm square. C. Should not be less than 245.35 mm square. Or D. Should not be less than 307.75 mm square. So what will be the correct option? So if we see here, the width of the section provided B is 400 mm. Okay, the effective depth of the section provided is 450 mm. Okay, the design torsional moment, which is basically 120 kilonewton meter. The design shear force, it is basically 50 kilonewton. The spacing of the shear reinforcements, so that is equal to this one. So it is 130 mm, and the characteristic strength of concrete or FCK value is 25 megapascal. Okay, so these are the values, and apart from them, the characteristic yield strength of steel is 415. So Fy is 415 megapascal, and percentage of tensile steel PT value is 0.25%. Okay, so it is 0.25%. So we need to find out the minimum area of total transverse reinforcement, ASV minimum. So that is equal to tau V minus tau C into B into SV by 0.87 Fy as per IS 456, right? So for this, we will first need the tau V value and tau C value, and for tau V, we will basically need the V value. This, okay. So equivalent shear force V, that is equal to Vu in plus 1.6 into Tu by B. So Vu is 50, Tu is 120, and B is zero point 0.4. So substituting, we get the V value as 530 kilonewton, and dividing that with width and depth, effective depth. So we get 530 into 10 cube by 400 into 450 equal to 2.94 megapascal. So that is the equivalent normal shear stress or tau V value. Okay. So that is the tau V value we got. And from table 19 of IS 456 2000, we get the design shear strength of concrete, or the tau C value is 0.36 Newton per millimeter square for a 0.25% PT value. Okay. So tau C is 0.36. Okay, and B is 400, SB is 130, is 0.87 into Fy is 415. Okay, so substituting the values, we get the ASB minimum is 371.58 millimeter square. So the minimum area, so it should be more, not less than 371.58 millimeter square. Okay, so therefore this, okay, so B is the correct option, should not be less than 371.58 millimeter square. So B should not be less than 371.58 millimeter square is the correct option. Okay. Fifth question. In case of a rectangular beam section, one of the following ways that may be considered as a remedy to reduce the effect of torsional shear is: A. Decreasing section width. B. Increasing section width. C, reducing reinforcement diameter, or D, increasing reinforcement diameter. So what can be the remedy? What can act as a remedy for reducing the effect of torsional shear? Okay, so what can be the remedy? So if you remember, in the example problem, so the moment we increase the section width, okay, so moment that we increase the section width, we were able to reduce the effective depth. Okay, so we were able to reduce the effective depth the moment we increase the section width. So there, that means, you know, in a rectangular section, so increasing section width can be a remedy. Okay, because that automatically reduce the effective depth or the overall depth and made the section economical. Okay, so increasing section width can be the remedy for reducing the effect of torsional shear. Okay, so therefore, yeah, so therefore, and also from here also we can find this. Okay, so if you see here, the v equation. Okay, so yeah, so if you see from here the torsional shear, from this equation, so this equation are also from this equation also, so it is always in the denominator. Okay, so this value is always in the denominator, so more will be the value of b. Okay, lesser will be the value of this total, the equivalent moment due to torsion. So more will be the value of b, lesser will be this value. And similarly here also, if you see, more will be the value of b, lesser will be the value of this. Okay, so therefore we can say the increasing section width can reduce the effect of torsional shear and act as a remedy. Okay, so effect of shear developed due to torsional moment may be reduced by increasing width of the section considered. Okay, so therefore b, increasing section width, is the correct option. Sixth question. As per IS 456-2000, in absence of test data, total shrinkage strain for design may be considered as A, 0.00050, B, 0.00045, C, 0.00030, or D, 0.00025, which is the correct option. So for this, we can refer to clause 6.2.4.1 of IS 456-2000. So here it says that in absence of test data, the total shrinkage strain for design, it may be considered as 0.00030. So that is C. Okay. So therefore C is the correct answer. Okay. So C, 0.00030. Okay. That is the correct answer. So that is the total shrinkage strain. Okay. For design, we have to consider in absence of test data. So 0.00030 is the total shrinkage strain assumed for design, considered for design in test data absence. Okay, so C, 0.00030 is the correct option. Seventh question. Modulus of elasticity and total tensile strength of M25 grade of concrete as per IS 456-2000 is how much? A, 25,000 megapascal and 2.5 megapascal respectively. B, 35,000 megapascal and 3 megapascal respectively. C, 35,250 megapascal and 3.5 megapascal respectively. Or D, 37,500 megapascal and 3.5 megapascal respectively. So which is the correct option? Okay. So the grade of concrete is M25. The characteristic strength of concrete FCK is therefore 25. Okay. So these are the formulas as per IS 456 for modulus of elasticity, EC value, and basically they're all short term. Okay. So when we refer to modulus of elasticity, always we refer to the short term. Okay. So the EC value in short term, it is 5,000 square root of FCK. So when modulus of elasticity is mentioned, it is always referring to the E short term value. Okay. So this EC value is equal to 5,000 square root FCK, and the tensile strength of concrete. Okay, so that is 0.5 square root FCK. Okay, so flexural strength is 0.7 and tensile strength is 0.5. Okay, 0.5 root FCK. So FCK is 25, or square root of 25 is 5. Okay, so 5,005 is 25,000. That is 25,000 megapascal value for EC, and 0.5 into 5 is how much? 2.5, right? So there is 2.5 megapascal, the value of tensile strength, or FCR. Okay? So if we compare 25,000, 2.5, so A is the correct option. Okay, so A is the correct answer. So therefore A, 25,000 megapascal and 2.5 megapascal respectively is the correct answer for modulus of elasticity and tensile strength of M25 grade of concrete as per IS 456. Okay. Eighth question. In absence of test data, the creep coefficient theta at the 28 days age of loading as per IS 456-2000 is A, 2.2, B, 1.6, C, 1.1, or D, 1.0. So which is the correct option? So for this also we can refer to clause 6.2.5.1 of IS 456-2000. So here also it says that in absence of test data, the creep coefficient at the age of 28 days, okay, uh, that is basically of loading, that is basically taken as 1.6. And what is creep coefficient? That is basically ultimate creep strain divided by the elastic strain at the time of loading. Okay, so that is the creep coefficient. Okay, ultimate creep strain divided by the elastic strain. Okay, so yeah, so that is the creep coefficient value theta. So in absence of test data at 28 days, it is taken as 1.6, right? So that is the value. And so if you see, if we compare here, so if we compare here, so the B 1.6, okay, so that is matching the condition. So therefore B 1.6 is the correct option. Okay. Ninth question: a rectangular beam section having width of 300 mm and overall depth of 450 mm is subjected to a design torsional moment of 120 kN meter. Additional shear developed in the beam section due to the torsion moment will be how much? A 540 kN, B 640 kN, C 690 kN, or D 700 kN. So here we have to find the additional shear developed, okay, due to the torsional moment. Okay, so that is 1.6 T by B. Okay, as you can see here. So B value is given as 300 mm, capital D value is given as 450 mm, factor torsion Tu is 120 kilonewton meter, and therefore we need to find the additional shear developed. So that is basically due to torsion. Okay, so that is basically VUT. Okay, so that is equal to 1.6 Tu by B. So Tu is 120, B is zero point 0.3 here, because we have to cancel the units. Okay, so therefore 1.6 into 120 by 0.3, that is equal to 640 kilonewton. So the additional shear developed in the beam section due to torsional moment is 640 kilonewton. It is B. Okay. So B is the correct answer. So B 640 kilonewton is the correct answer. 10th question. A rectangular beam section having width of 300 mm and overall depth of 450 mm is subjected to a design torsional moment of 120 kilonewton meter. Additional bending moment that need to be considered in design of the beam section, okay, will be how much? A 110.78 kilonewton meter, B 120.54 kilonewton meter, C 176.47 kilonewton meter, or D 180.67 kilonewton meter. So we need to, like the previous question, we calculate the additional shear developed. In this case, in this question, we have to develop, we have to find out the additional bending moment. Okay, so that is nothing but how much? It is Tu into 1 plus capital D by B by 1.7. This one. Okay, so that is the for value we have to find out. So here also B value is 300 mm, capital D is 450 mm, Tu, that is the design torsional moment, is 120 kilonewton meter. So therefore additional moment due to the torsion, this one torsion, okay, acting, that is equal to Tu into 1 plus D by B by 1.7. Okay, so Tu is 120, D is 450 or 0.45, and B is 300 or zero point 0.3. Okay, so we can tell either in meter or millimeter because we can cancel it anyways. So therefore the additional moment due to torsion MUT is 120 into 1 plus 0.45 by 0.3 divided by 1.7. Okay, so yeah, so the value comes out to be 176.47 kilonewton meter. Okay, so that is the additional moment, so it is matching to option C. Okay, 176.47 kilonewton meter. So here, therefore option C is the correct answer. So C 176.47 kilonewton meter is the correct answer. Okay, so yeah, so with this we come to the end of today's discussion. Okay, so I think we have almost covered the main all the fundamental main design philosophies related to reinforced concrete structure. So next class we will be discussing on how to apply these philosophies in the design of multi-story, okay, multi-story building or high-rise structure. Okay, so let us see how these design philosophies can be applied there for designing multi-story building. So for that we will be using for that that will be shown in some software. Okay, so it will be shown, the analysis will be shown in some through some software for like a brief understanding. Okay, so for us a little understanding. So that is not the main core main main scope of this course. Okay, so this is basically the very preliminary, very basic version of designing of reinforced concrete structure. So that is just for a demonstration. Okay, so how to apply this philosophy in the design of high-rise structure. Okay, so we will see that in the next class. So yeah, so with this, let us end today's discussion. Okay, and have a great day ahead, and great week, coming week ahead. So with this, let us end today's discussion. Okay, so yeah, so bye.